Hello, and welcome to this webinar from the Register. 12 reasons why your AI initiatives need vast data for NVIDIA SuperPOD, in which we'll learn how a scalable SuperPOD solution can accelerate your AI adoption journey and seamlessly integrate AI into your business operations. Now, organizations across all verticals and industries now recognize the need to adopt AI, but many businesses worry that they will struggle with the complexities of building and deploying AI solutions. They want a turnkey platform that can be supported by their own IT teams. NVIDIA DGX SuperPOD on the vast data platform is designed and built to meet that very requirement. It has 12 key AI transformative capabilities that enable organizations looking to build AI solutions to overcome traditional AI deployment inhibitors and meet their business objectives with existing resources. I'm James Hayes, and your host for this webinar, and with me to explain how this solution achieves its objectives, I'm joined by two vast experts. Jeff and Jan, welcome to the webinar.
Hello, James.
Hi. Let's begin our discussion by briefly filling in a little bit about the background of the partnership between Vast Data and NVIDIA for webinar viewers who are not familiar with it. Jeff, perhaps I can come to you first of all. Could you tell me a little bit about how the two companies came to join forces?
Sure. Yeah, actually, we have been working together since our inception. There was a team that was acquired into NVIDIA, a networking team for a company called Mellanox, which is now the basis for all the networks for the SuperPOD infrastructure. And many, many years ago, we realized that a technology that they had been developing called NVMe over Fabrics could be instrumental to building a new distributed systems architecture that we built now that we call DAYS. And so since day one, we've been working together. We've extended our partnership to essentially find new opportunities of collaboration throughout the years. We added support for an API called GPU Direct Storage, which is ideal for moving data really quickly into GPUs. We added support for Bluefield, which is their next generation data processing units, basically a processor embedded onto a network adapter that you can use to do things like control SSDs. Mm-hmm. And so yeah, it's been a very robust and good spirited engagement that we've had.
Great stuff. Okay, well, let's move on to our 12 capabilities. We've broken them down into sort of subgroupings to sort of reflect the technical attributes that they embody. The first one we're looking at is enterprise resilience. We're looking at how resilience is deployed across the platform. We'll go through them maybe one at a time. We've got resilient controllers, power loss resilience, drive loss resilience, and unified code base. Just can I open the conversation by asking you about resilience and resiliency generically? How has platform resilience moved to front and center of enterprise IT requirements? I hear resilience mentioned a lot these days. Why has it become so important in terms of defining IT infrastructure and the kind of performance levels that organizations are trying to reach?
Yeah, so but I think the thing to understand is that scalability has largely been the enemy of resilience. If you think about some of the more scalable compute infrastructures and storage infrastructures that have been introduced into the world, customers have been largely conditioned to think that as you go bigger, you just have to assume a certain level of fragility and instability. And the funny thing about what NVIDIA is now promoting, and if you watch how people are doing things like training large models, large language models, and things like this, is that the infrastructure investments are massive. Some of these systems cost not just millions of dollars, but tens or hundreds of millions of dollars. And as they get bigger, if they become more fragile, that becomes kind of counterintuitive or counterproductive to an investment thesis, where it's, it just doesn't work for companies that are making these large investments if their systems are failing all the time.
Okay. Jan, would you add something to that? I mean, could you tell me a little bit about how resilience is actually being built into data storage management at a functional level? Is this representing a step up from previous generations?
Well, just to go back to the first point for a bit, resiliency is important because at scale, you will have to deal with errors. They become a certainty at a certain scale. So your system has to be resilient to withstand them. Otherwise, as Jeff says, you will be having your millions of investments not delivering any value. And that's why modern architectures have a focus on building resiliency into the system. And that's what systems from 20 or 30 years ago, like having a design principle from 20 or 30 years ago, have not built in that much. So with the new architecture that we have built, resiliency was kind of you could say a first-class citizen, right? We've thought the system with a resiliency mindset.
Yeah. And can you tell me a little bit about the resiliency you have around power loss and drive loss? What's special about that?
So we can, yeah. I was going to say we could get into all these. We've got like little, slides that we built to kind of, kind of spell all this out, James, if that would be helpful.
Yeah.
Okay, so let's kind of dig into the first topic, right? So if you think about, the way that people have been building SuperPODs up till now, they've been using parallel file system technology. And here, what you typically have are file servers that sit on top of storage controllers that each are managing a collection of JBODs, or as people call them in the modern era, JBOFs, just a bunch of flash enclosures. And you basically build pairs of controllers that manage some collection of JBOFs, and you kind of build a large namespace out using these file server, controller, and JBOF scalable units, right? And big systems can have, in certain cases, dozens or even more of these. Small systems can start with just one scalable unit. But the interesting thing is, if you think about the way that these systems have been built up until now, again, as Jan mentioned, a lot of the high availability characteristics were born really like 20, 30 years ago. If you think about just this idea that you could have two controllers that manage a collection of disks, like, I don't know, those concepts go back to the inception of companies like NetApp, which is now, more than 30 years old. And so, that of course is a design point which could be optimized. And then the other consideration is, as you look across these arrays of systems, what you don't have are any redundancy. So you can RAID within them, but you can't RAID across them. And as we thought, and Jan mentioned, if you think about building a system in the modern era where, an array is not the design point, but rather a SuperPOD or a data center scale systems infrastructure is the design point, what comes of this is a new type of systems architecture where you have a collection of containers that can all see a global volume of SSDs that live over that next generation storage fabric that I talked about that we collaborate with Mellanox on. This is called NVMe over Fabrics. And the step function change is that now you can have a whole sea of containers that can fail over across each other, and no one container owns any piece of data, and you essentially get N-way failure over, or N-way failure management. And then at the SSD level, all of these enclosures themselves are fault tolerant, but you can start to build large stripes of data even across enclosures so that you can support the failure of a full enclosure loss across racks or across, a whole cluster. And so, from an uptime perspective, you're just far less you're far less dependent upon any one machine being available at any given time, or any two machines being available at any given time. And you start to build to like data center class levels of resilience. Jan, did I characterize that right?
Excellent. And I mean, just to stay in the example, if you think you have two servers and they are redundant and one of them fails, the other one keeps up the operation. But if you have 1,000 servers and the two wrong out of these fail, then you have a problem. And of course, with an N-way redundancy, we can have dozens of failures in the server layer, and we will not lose any connectivity. And that's what resiliency at scale should look like.
But the other consideration, Jan, is if you have two servers in a array pair, and one of them fails and you're running both simultaneously, then, you know, from a striped file system, the total performance goes down by half. Whereas, you know, I didn't think about this when I originally put the slides together, but here, you know, your performance goes down by n-1 in the case of a container failure, as opposed to the previous example.
And that's the second aspect of resiliency, right? I mean, the resiliency we typically think in, is my data available or not? But performance resiliency is another aspect of resiliency. So if your SuperPOD is running and it costs you millions and you lose half of your storage performance, then your SuperPOD might run at half the speed, whatever your application is doing right now. But that's another aspect of resiliency. How performant are you in the state of failure? Because as I said before, at scale, you will have to deal with that situation frequently.
So what comes of this is something that is, you know, just far superior from both a file server perspective and from an SSD failure perspective. Now, the other one that's interesting is around power loss. And one of the ways that these machines end up, you know, providing decent performance from a write bandwidth perspective is by ordering data in some DRAM-based write back cache. Now, RAM is volatile, so you need to maintain a collection of batteries in order to support that kind of power management and destaging cache from RAM to some sort of SSD, or, you know, for older systems, they would destage to hard drives. But, you know, we work, you know, in a fairly large company. VAST is now about 550 people around the world. And we have a few people that have come from enterprise organizations that have, you know, deep experience building cache management systems and legacy architectures. And we know of one that requires something like 1 million lines of code in order to move data from DRAM down to SSDs in a way that is fully consistent. And this code is probably some of the most fragile from an R&D perspective, in terms of like getting it precisely right, so you never lose a drop of data as you move data down from cache into SSDs if you're dealing with some power loss event. So, you know, the interesting thing about a lot of these large scale SuperPOD systems is that the power requirements are just off the charts, and that can result in some kind of interesting situations when it comes to just keeping up data center power. And, you know, my thesis from a design perspective is cache destaging is a little bit of a black art. And I would argue that there's really like no code out there that is entirely bug-free. And you see it in even some of the most popular enterprise transaction processing arrays out in the marketplace. Now, if you kind of compare that to this modern architecture that we've been talking about with VAST, what you have is a collection of containers that have no cache in them whatsoever. So you don't need any batteries or anything like that. And at the SSD level, it's fully persistent, right? Your data is first persisted in a write buffer made of storage class memory, and storage class means that it's non-volatile, and then ultimately destaged down into low-cost QLC flash, which is equally non-volatile. So there arguably is no recovery code or no destaging code within the system, and there's no batteries or anything like that that's needed, just because everything is a persistent write. I don't know. Go ahead.
Yeah, and looking at that, of course, all the systems are, any system that you can find in a serious enterprise offering is dual power supply, is redundant in that sense. But anyone who has more than, I don't know, a few years of experience has seen these events where power is lost, right? And where things go wrong. And the best prevention is not to have any data at jeopardy at all. That's the best way you can protect yourself from these things. And as Jeff mentions, no caches mean no batteries. I mean, anyone who had to deal with those, they have a limited lifetime. They sit in data centers of 35 degrees these days because power efficiency or cooling efficiency is important. Batteries are a constant issue when you have to manage them, especially at scale. And we come back to the scale aspect again. You're not managing 2 batteries or 4 batteries. You're managing thousands of batteries at some point if your system gets large. So taking all these components out is a major impact on resiliency.
I never understood the temperature impact for battery management. What about supercaps, Jan? Is that the same?
Well, it
same
depends.
consideration?
Well, it depends on the system's design. If you really think a modern storage controller that runs in a 1+1 configuration, these are PCs, these are servers, right? They have powerful x86 CPUs. So powering them on a supercap is not really going to work, because what you have to do, you have to power a whole computer for a long time.
Well,
Batteries do that. The alternative, your supercap only powering your memory and buffering it for, as we have seen it, I don't know, 15 years ago, like 3 days or 4 days, putting you at risk. What if you can't fix the problem within that time frame? So I don't know. I don't think that supercaps are really a resolution. People have worked with non-volatile memory as a replacement for the DRAM, right? Then you get the benefit of a persistent storage. But in a single server, you can't scale easily the performance of a non-volatile memory chip. So you're then limiting your performance to that performance of that single DIMM or the two DIMMs that you have in that machine. So there is catches to that, I would say.
Got it. I've seen, just SSDs with a little bit of, DRAM cache on them, but you might have something like 10 supercaps just on a single 2.5-inch device.
Oh, and so supercaps are expensive. Don't forget about that. I mean, it's...
Oh, sure. Sure. Okay, so, let's move beyond that altogether, and let's just have a system without cache, which means no batteries, no supercaps, no... you could have hot data centers. Well, reasonably hot, I guess. No. Our customers are going to crank up or crank down the air conditioning, and they're going to start yelling at us. Okay, so then the next consideration really is around drive management, right? And I think it actually gets pretty interesting, this discussion. And if you go back, get in the Wayback Machine, we were talking about hard drives something like 5 or 10 years ago, and how 20 terabyte drives are really challenging to conventional RAID codes. And I think we've all kind of moved beyond hard drives for the most part. If you think about SuperPOD, there is no single architecture that has support for hard drives. But even in the case of SSD-based systems, you're now to the point where areal density is far, far outstripping what you'd ever be able to do with hard drives. And so by the end of this year, there are a number of enterprise SSD vendors that are talking about 60 terabyte devices. I've even heard some discussion around 100 terabyte SSDs in the not too distant future. And so I think that then casts a new light on different failure protection modes and erasure codes and RAID algorithms, for reasons that, you have a lot of data that needs to get rebuilt when one of these devices fail. And so rebuilds take a long time. And if you have compounding rebuilds, then this becomes a little bit tricky. And in our case, what we've done is we've pioneered a new code, a new erasure code. And this code, it essentially doesn't work like classic erasure codes do, where you have 2 copies of the same parity within a RAID stripe. And if one of those drives fails, you can use the other one with the same exact parity information. In the case of VAST, we've developed this new type of code called a locally decodable code. And what it allows us to do is to dramatically accelerate the time to recovering a lost device or a lost block by having different data in each of the parity devices. And each parity device is essentially there to represent a fraction of the stripe. And so essentially the fractions that you have to rebuild are proportionate to the number of redundancies that you have within a write stripe. But the cool thing about this is that, we can scale up the kind of the failure protection domain up to 146 plus 4 blocks within a large cluster. So our, classic RAID stripes look kind of like 8 plus 2. But now you can go to 146 plus 4, which means you only pay 3% for data protection overhead. This is an industry low. But on the flip side, once you start going beyond plus 2 with respect to data protection or drive failure protection, you start adding exponents of resilience. So at 146 plus 4, you can have essentially 4 things that can fail within a stripe and still be entirely online, which is just more availability. And if you combine that with the rapid rebuild codes that we built that we call locally decodable codes, you essentially get to 60 million years of mean time to data loss. while only paying 3% for data protection overhead. And so now we don't really worry about devices in the range of 50 terabytes to 100 terabytes. All of this becomes completely okay with this new style of error correction. And I have to say, I'm thinking I don't think I've ever seen a system with more than 2 drives having failed within a protection group at any given time. And I think part of that comes from the fact that it's fail in place. So you don't have to wait for a replacement drive for the system to start rebuilding. It just does that instantaneously upon the loss of a device. It kind of rebalance the data across all the available devices. So it kind of erodes over time until you replace the failed SSDs.
No, looking back and completely anecdotal, the reason why people lost data on their systems, double failures not being replaced with new devices were a problem. So failing in place is important because that gets you an additional layer of resiliency, so you don't have to manually intervene in your system. So that's definitely an important thing to resiliency. And the other thing, of course, these large devices, no matter if they are disks or flash, I mean, both are kind of affected. If they get larger, you need more resiliency, and +2 is not enough to get that at all circumstances. And coming back to the early part of that call, James, you asked about the resiliency and architecture and how they play together. What we have done here is not something you could do in a legacy architecture, right? You cannot go and do your 8+2 and now go 146+4 because you need to deal with your IOs completely differently. It's simply not possible to retrofit this, let's say it like that. So you need a new architecture. We have built that to get to that point where we can deliver all these benefits.
I tend to think about the biggest enemy of drive failure being customs. As I think about building a global global company, right? You know, that's always the thing that gets you, is trying to get something in and out of a different port.
And this is always forgotten in the meantime to data loss calculation, right? Where you calculate how quickly you replace a drive before the next one can fail. Add a week of customs.
Right. So you know, our partners have support depots all around the world, but you know, it seems like these logistical problems are always, you know, kind of like Murphy's Law as you think about how to go and build a robust system.
But it's like with the caches, you can have redundant power, or you cannot have volatile data that you can lose in case of an emergency. So that, again, this is how you build your architecture, builds your resiliency.
Mm-hmm. So speaking of architecture, it's probably not really an architectural discussion, but it is at least an engineering discussion. You know, the way that we see all of the SuperPOD offerings that are in the market up until now, what you have is a series of file systems that are layered on top of some third-party storage controllers, and you kind of have these kind of glued together with some glue code, right? And in certain cases, some of these file systems are just volume aggregators that sit on top of things like local file systems. You know, local file systems like ext4 or XFS or ZFS or solutions like this. And so from an engineering perspective, it's actually a lot of stuff to keep track of, a lot of stuff to get right. And so what comes of that is you have like a whole layer cake of QA complexity that comes with it. The APIs are always not entirely designed for each other. And so you have to get that right. And from a management perspective, there's just a lot that needs to be managed from a code-based perspective. And so, you know, for support organizations, these are a lot of different places to look for issues, and it can be extremely complicated. And now, if you take a different approach to building systems, you know, we started from the perspective of, well, let's just build a system that's made of one stack, where there isn't independent RAID controllers, where there isn't independent local file systems, where there isn't an independent file system that sits on top of all of that, but it's just one unified stack where the logic runs in containers. It's one OS, one stack that is both file and object storage. And all of that container code just manages a collection of SSDs that are on the other side of this NVMe fabric. And what comes of this I think is a much simpler environment to maintain and to support. And we're seeing evidence of that as we deal with customers in the field, and they have the occasional support issues that come up. We can actually navigate these situations much easier than my past experiences showed that you could. And on top of it, it's just, it's one place to look for issues. It's one place to QA against. It's one place to build a management framework on top of. And so this is, I think, a pretty big difference between how SuperPODs are built today, or have been built up until today, Jan.
Yep. No, you said it well.
Okay. Cool. So that kind of caps off the resilience discussion, right? You've got a system that is entirely developed in-house. There's no dependencies upon open source code. It's easier to develop, easier to QA, and you just get to much better resilience than what you've had in the past. James, anything we didn't add that you would like us to talk about there?
Not really. I think you've covered off all of the aspects of resilience really well there. Very rounded response. Is this a good point at which to move on to some of the other capabilities about SuperPOD, such as its efficiencies, its enterprise-grade efficiencies? Perhaps you could tell us a little bit about how they stack up.
Sure. Here, we see a variety of other considerations that come in that are less about just keeping systems online, but rather about keeping them affordable. And in particular with efficiency, VAST was a company that was built not necessarily for performance density. A lot of people in the SuperPOD space talk about things like, oh, we can get the most performance out of an SSD, and that's great for your AI training engine. But on the flip side, if you think about what is really happening there is that cost density becomes completely intertwined with performance density. And we looked at it and said, well, what if we weren't to build the fastest system from a single SSD performance perspective, but rather what if we built the most affordable, such that customers could afford to essentially not just build small concentrated flash environments for their SuperPODs, but rather could afford to have all of their data be layered on top of a low-cost, scalable flash system. What comes of that is that you don't have data that's being moved back and forth from your archives anymore, and you just start computing off of your archive. And so that becomes a real game changer for people in terms of not just efficiency, but also simplicity. And what we see is that applications really benefit from that, but there are a few ways that we go about accomplishing that mission. Okay, so let's talk about the first of those. This is a discussion around a new type of flash that's called QLC. QLC flash is definitely the most affordable path to deploying flash within a storage environment today. But the ways that you have to write to these flash drives change considerably. And the reason for that is something that's called an erase block. And so if you think about a block of storage on a standard storage device, particularly with flash, most people want to get IOPS or random performance out of these devices. And very few people deal in 1 gigabyte increments in terms of the type of data that they're working with, right? If I just take like some amount of text that I'm using to build a large language model, or even if I'm taking a tile of an image that I'm using to build a computer vision model, never are these 1 gigabyte in size. But these new flash drives, they like to be written to in 1 gigabyte blocks. And if you write anything less than that, you want to go, let's say, do an update to the drive and maybe delete a small portion of that 1 gigabyte. Well, the whole 1 gigabyte needs to be overwritten in order to free up space. That's why it's called an erase block. And so there's some kind of odd things about these new QLC devices that I think people that aren't practiced on flash really don't necessarily understand. First of which is that there's just a limited number of the times that you can write to these drives. And so there's only about 2,000 write cycles for these devices. The way that they get good capacity is you start to layer a bunch of data within a cell. And as you have to write up more and more layers, you have to charge that cell with even more voltage. And that kind of starts to play hell with the structures of the silicon. And so More voltage means that you have a shorter life expectancy in terms of the number of writes that the device can handle. And what happens is that, systems need to write smart down to these drives. And they do that through buffering, and they do that through basically making sure that you fill up a full 1 gigabyte stripe as you write it down to the system. But the challenge then becomes, unless you've organized data within that erase block that has data that has a common life expectancy, as you want to go and delete some of your data, well, that requires you to go into that erase block, delete part of it. And if you want to actually get that capacity back, then the good data needs to be written elsewhere in a flash drive. And deletions and appends really, really hurt. And the problem becomes journaled file systems only really know how to write and overwrite data in place. They're not designed to accommodate for the idiosyncrasies of these drives. And so for the most part, any system that does support QLC flash that uses these journaling technologies will basically just completely, put the burden of flash ownership at the feet of the customer, where it's up to them to basically deal with the risks and the limits inherent with those systems. And the interesting thing is, as your systems fill up more and more, as you get closer to like 80% or 90% full, then the system becomes under pressure to go and invalidate blocks and move data around in those flash drives even quicker. And so what happens is that the systems vendors that ship journaled file systems into these environments using QLC flash will ask that the customers don't run their systems anywhere near full, because it will wear the drives out prematurely. And so, for that reason, we started from a different perspective, where we said, okay, well, what if you could build a new type of system that wasn't just log structured, where all of the writes down into the flash drives happen not in place, but all the writes go into some new write stripe in the way that you could think of like a database works. But on top of it, what happens is that we can categorize data according to its perceived life expectancy. And after the data has been written into a write buffer, it then flows down into low-cost QLC flash, organized in erase blocks where all of the data in that block has a common life expectancy. And that allows us to really minimize the amount of overwrites or garbage collection events or write amplification events that have to happen in storage. And what comes of that is a system that ultimately allows us to provide 10 years of guaranteed endurance on top of this low-cost flash infrastructure. And so, I think this is the most critical thing. You have pretty much any storage system invented almost since the dawn of time. If the slot is compatible on that storage array, you can put an NVMe device in it. You can put a QLC device in it. But there's a big distinction between being able to support a drive and also being able to provide 10 years of endurance of these drives. As I think about it, we typically go and we poll our fleet of systems that we've got in the field. And last I checked, there was no system deployed since the 4 years that we've been shipping equipment that's used more than 10% of the endurance of those drives. And on the flip side, we kind of hear horror stories about other technologies that weren't designed for QLC that will wear these drives out. Particularly when you run them really full, they wear them out in the span of just a few months or a few years. And so I think that caused the industry to take a pause on QLC, and people are now just starting to get back into it. But really need to understand the characteristics of your workload, how full you want to keep your systems before you kind of take the path of using this new type of QLC flash.
I think for our customers, the only thing they need to know is we guarantee the endurance of the QLC, because all claims are invalid if your vendor does not stand up for that promise, right? I mean, we can talk all day about how we optimize stuff. If we don't pay the bill, if things go wrong, then it doesn't mean anything. And if you think about the layered architecture that Jeff introduced or showed about what is used today, where you have a block level with a RAID array, and then you have a local file system, all these things, If you want to optimize that for QLC, you have to optimize all these layers, and they have never been made for this. I mean, RAID systems work on chunk sizes of 256K, maybe 1 meg or 2 meg, but that's far below what the 1 gigabyte is that you would need here. And if you would turn them into 1 gigabyte chunks, then the performance would go down the drain. So, but all a customer needs to know is, well, it's a QLC offering, but with the guarantee for the endurance. Because there's other QLC offerings there, and there's a lot of fine print around them. Who pays for the replacement drives, or how can you use the system? What can you not do to the system? We don't do that. So,
yeah, and that's in our standard terms. But Jan, I've seen customers say, well, if I lose a few drives, it's not really a big problem. I'll pay for that.
Yeah.
And what they don't realize is that,
yeah.
If you've got a striped file system, all the drives kind of wear out around the same time. So it's not just losing 1 or 2 drives. It's basically being up a creek.
Yeah, they will all fail at the same time, and that's going to be a problem, because no resiliency level in your system will prevent you from that. Then you go back to your tape and get your backup, which you hopefully have.
You can't do AI off of tape, though. Okay, so the next consideration is one around data reduction. All right, so the objective is first to take low-cost flash, apply that industry low data protection overhead down to storage, so that you really start from a low-cost basis. But once you get there, what we realized is that there's just a ton of opportunity that you can realize with random access media if you look for patterns in a new and interesting way. And the important thing here is to understand that, there are a variety of SuperPOD offerings that will advertise capabilities like compression. But the problem with compression is that it's very limited in terms of its ability to find patterns within data. And half the time, customers are storing pre-compressed data in the system already. And so it's very difficult to run a compression mechanism or method on top of a compressed piece of data. And particularly if you're using the same method, you're not going to find any gains. And so there are different things that can be done. Compression is one of those, of course, but as I mentioned, compression very often, it only works on a localized basis. It is fine grained. You can go down to a few bytes in terms of the pattern matching, but it never goes across all of your data. And that's why deduplication was invented. Deduplication works via a hashing algorithm. And that hashing algorithm, essentially, it limits the amount of granularity that you can get to, because those hashes have to be held in memory. And memory is expensive. And so you don't want to hash at 1 byte blocks, just because you'd be spending more in memory than you're saving on deduplication. And so typically most systems will hash data in the form of like 32 kilobyte blocks or so, which is much, much more coarse than what you have with compression. And what we've invented is a new style of pattern matching that is called similarity. And what similarity does is essentially allows us to go in and look across all of the blocks within a cluster and essentially scan them, not necessarily for exact matches, but rather to scan them to see if there are any blocks that are similar to each other. And once we find that these blocks are similar to each other, what we'll do is we'll group them into what we call compression groups, which are known as similarity clusters. And then every new byte that goes into that cluster is essentially delta compressed against a reference block using a compression algorithm that comes from Z standard, with optimizations that are actually well suited for artificial intelligence workloads. And so here, what you have is essentially a global reference compression system as opposed to a global deduplication system. And once data ultimately gets stored down to QLC as it rolls off of the write buffer, on average, our customers see somewhere in the form of roughly about 3-to-1 data reduction. And at 3-to-1, what you've done is you've completely covered the gap between hard drive economics and flash economics if you've applied our low-cost data protection codes on top of QLC flash. And so, I'm a big believer that if you kind of apply new concepts on top of new technology, there's really some special gains that can be achieved. And this is definitely one of the more interesting things that we do from a computer science perspective. And just like the QLC discussion, we've actually guaranteed that our our level of savings will be superior to anybody else's in the marketplace who will pay for the difference in free storage. Now, one of the other interesting things about this is that it also saves considerably with respect to power. I'm a big believer that data reduction saves on an absolute basis the amount of power that you need to go and deliver for storage infrastructure. And so both of these kind of come together, cost savings and power savings, when you consider this new approach to savings that we call similarity.
And in none of the SuperPOD traditional ways, any data reduction is actually used. I mean, all of these systems come from the HPC space, and the attitude was, as Jeff said, the data is pre-compressed anyway. So why would I add another effort to try to compress it? And deduplication basically is an enterprise technology. It's great to save some storage space, but it destroys your performance, right? And if you're considering if you're in the game for performance, then you don't do that. So that was kind of the attitude towards these parallel file systems. But with a new architecture, you get new abilities, and that's how we could build it into a platform that delivers SuperPOD performance and still reduces the data in the backend. And on top of that, you get the flash performance, right? I mean, you just talked about 3-to-1 gets you to hard drive economics. So then the flash characteristics of performance is even a benefit on top of that. So.
But it's totally a virtuous circle, Jan, because the reason that deduplication didn't work for high performance systems in the past was that it would fragment your drives. But with flash,
exactly. Yeah,
you get that random access, which allows you to reduce down in new ways. And this thing kind of goes on and on. Okay, so, and then the last consideration is, if you think about this idea of all of these systems that are independent, all being stitched together by some sort of volume aggregator, servers can fill up differently as you have clients running into different servers. The backend SSDs fill up at variable rates, and this creates performance hotspots. In our case, this new architecture that we built allows all the servers to have the same global access where you can eliminate hotspots. And then we kind of spool data from all of these servers across the SSDs in a very balanced way, such that, you never have to worry about rebalancing the system, which is very common with HPC technologies. So what comes of it is just no stranded performance. Okay, so the last topic that we'll breeze through pretty quickly is simplicity. And I think here we kind of did the math on, well, what if you had a parallel file system environment? What's the management complexity associated with that? Well, the file systems themselves, they're a global namespace, so they have a global login. But on the flip side, the infrastructure that underpins those systems each have their own independent management consoles, their own independent logins. If you have systems that are built on virtual machines, then they themselves also have their own logins. And what it could mean is that for a system that has like 10 arrays in it, you could have to go to as many as 40 different consoles just to administer your system. Now, in our case, it's just one login that also supports things like non-disruptive expansions and non-disruptive upgrades. And these are capabilities that people that have come from the HPC space, which is, HPC technologies were the only things that were supportable for SuperPODs up until now. They haven't even become, accustomed to, or you didn't even know were possible. And Jan, I don't think you've been here long enough.
It's exactly my story. I have done Lustre, GPFS, BGFS in the past, parallel file systems, and it was always an accepted thing that, no pain, no gain, right? So it's for that extreme amount of performance, you need to have it a bit more complicated, right? You need to upgrade these things individually and to stack one by one, and it's a long upgrade plan or whatever you have. And then I joined Vast, and I didn't want to believe it, but there is a way to one-click upgrade your large-scale system. I'm converted now. I believe it now because I've seen it, but I know that many people out there don't believe it, that you can upgrade your 1 terabyte per second system the same way you upgrade your NetApp or even your Synology NAS at home, right? That's seriously a bit of a game changer.
What I was wondering if you've seen one of the emails that come from Ren and our CEO that say, every once in a while I have to remind everybody that there are no offline upgrades. And, those emails come out about once a year. But, he basically says, like, if anybody wants to get an answer to that question, come and ask me, and I'll always give you the same answer, which is a no. Okay, so now you've got a system that is efficient, it is resilient, and it's also super simple. And my thesis is, a lot of times this market can get into a gunfight around performance, but if your system isn't online, whether it's for resiliency purposes or whether it's just for upgrade or expansion purposes, then there is no discussion about performance. And this is something that I think the speed freaks in the market don't necessarily fully appreciate. And so, we've been operating for the better part of 4 years now in the market. Our uptime is roughly around just a little bit under 6 nines of availability. And yeah, so we couple that with what's known as a white glove support experience, and what customers get is something that they've just never had from a SuperPOD experience. That's our story.
Great stuff. Jan, is there anything you would just like to add to that in conclusion?
No, I think we've gone extensively over all the benefits that we offer. And simple, resilient, efficient, and performance is just the outcome of that whole platform.
Great stuff. Well, unfortunately, we've just about used up our time for this Register webinar. So I want to thank our two excellent speakers, because I've certainly learned a lot in the last 40 minutes I found fascinating and interesting. Jeff Denworth, who is co-founder and CMO at Vast Data, and Jan Heichler, who is International Alliances pre-sales leader. Thank you both for sharing your expert perspectives with our webinar audience today. We hope that you've learned plenty of things that will inform and guide conversations concerning your adoption of AI-powered data storage initiatives, wherever they lead you. And with that, until next time, goodbye.